So I'm very happy to be here. Let me thank the organizers for the invitation. And the talk is on designs in symmetric spaces. I'll explain the notions. Okay, so let's start with an example. So we take the one-dimensional sphere, the circle, and we just parameterize by the interval 0 to pi, and we want a small number of points on which every low-degree polynomial averages to its global average on the circle. Meaning that if I average this polynomial on the points of the set D, I get the integral, right? With respect to the normalized measure of the circle. So of course, the constant functions satisfy this trivially. So what we need for any k between 0 and t is the upper bound of the degree of the polynomial. We need both cosine k phi and the sine of k phi to average to 0, right? And we want the smallest number of points for which is holds, and it's easy, right? For t equals 1, only for sine and cosine, we can take our set of points to be 0 and pi. We have this trigonometric identity. For t equals 2, we can take 0, 2 pi over 3, and 4 pi over 3. Right? And in general, we can take for any t, we take an equipartition of the circle into t plus 1 points, and it's a minimal solution. Any equipartition will give a solution, and it ends the best possible. Right? So, as a point of view, let me think about this as trying to approximate, we have a space, the circle in this example, and we try to approximate it by finite, but small subset. Right? So, what we have is that every simple function, a polynomial of degree at most t, averages on D to its global average. And since products of two polynomials of degree at most t, a degree at most t over 2 is a polynomial of degree at most t, if you restrict to D, so also the inner products of two polynomials of degree at most t over 2 would average to the real inner product, right? So the restriction to D captures the Euclidean structure of the set. So it's very nice, right? And I can approximate a circle by its equipartition. So in this sense, D gives an approximation, right, to the, if I may, the analytic structure, right, of the function of the circle. And it also provides a metric approximation, right? We have an equipartition of the circle, so we have a circle, right? And we divide it into this equipartition. So every point of the circle is approximated, is nearby a point of the equipartition, right? So we have approximation in two notions. It's metric notion and it's analytic notion. And what we are going to try and argue in this talk, that this happens for not only this one. Okay, so let's talk about spaces and designs in general. So we have 3 examples, running in this talk. The Euclidean sphere, the Hamming cube 0, 1 to the n, and the Hamming sphere, the Hamming sphere, of radius k, which means all the points in the n-dimensional cube which have exactly k volts. So these spaces are symmetric, meaning they have a large group of isometries. They have a distance transitive group of isometries. So if I have 2 pairs of points at the same distance, so if I have, point x and y in my space, and another couple of pair of points, x prime and y prime, and the distance between x and y equals the distance between x prime and y prime, then I have some isometry moving x to x prime and y to y prime. This is the distance positivity. And of course we have it for the sphere, right? You can rotate any way we want. We have it for the cube, and the isometries are shifts and permutations of coordinates, and we have it for the Hamming sphere, where the isometries are given by permutations of coordinates. All these spaces are sufficiently symmetric, and the design is a small subset of points definitely a finite subset of points in the space on which every simple function averages to its global average, and I need to tell you what the simple function is. Right? So just to say it formally, so we want a set D on which every function, the average of every function, every simple function over the set, equals the integral of the function with respect to the normalized invariant measure of the space. Okay, so what's a simple function? So we should start with a Laplacian. So a Laplacian is a linear operator on nice functions on our space X. For a graph, for a regular graph, we will take the Laplacian to be, for a regular graph, we take it to be D times the identity matrix minus A. This is the usual graph Laplacian. And for a Riemannian manifold, this is the Riemannian Laplacian of the manifold. We don't have to know what it is, but we have to know something about its eigenfunctions. So a Laplacian would have non-negative eigenvalues starting from 0, and each one of them would be a finite multiplicity. And the eigenfunctions of the Laplacian form an orthogonal basis of the L2x. This we have, and now we can describe what this notion of simple function. By the way, I will have it for questions if you have. So stop me and start. Okay, so what's a simple function? So let Vk be the eigenspace associated, finite dimensional eigenspace associated with the case eigenvalue. And then we have, so it's, as a point of view, we are going to describe the space of functions by, by uncovering these eigenspaces one by one, from the simpler to the more complicated. So the first eigenspace are just the constant functions, the second one corresponds to the first eigenvalue, and so on. Right? And the function is simple, is T-simple if it lies in the direct sum of the first T plus 1 eigenspaces. Right? So that somehow the intuition is that the functions become more and more complicated as eigenvalues. Right? We will call D a design of strength T if every T simple eigenfunctions averages to its global average. Right? This is a key definition. So let me just see if there are any questions. Sorry.
A bit more intuitive. Why one eigenfunction? Why second eigenfunction?
No. All these are, the spaces are not one-dimensional, right?
Yeah, but still, why is it?
So let
for
me,
the cubic polynomial.
in the examples, you'll see that these low eigenvalue eigenfunctions are really low. Usually they are logically polynomial. Usually, not always. Okay.
But for general graphs, there is no reason to believe that.
I don't know. For symmetric graphs, it's an empirical fact that this is right definition. Okay? It's a good question. I don't have a good answer for that. Okay. So this is the definition. Okay? This is the definition. So some history, just to throw it some history. This is a natural question arising, this approximating integrals by a small number of points arising in numerical analysis. The problem of the sphere actually goes back to the 19th century, and it was defined in a more abstract way by Delsarte for distance regular graphs, even for association schemes, but let's say we have a special case of distance regular graphs, by Delsarte, Goethals, and Seidel for the sphere, and by Dunkel for a more general class of symmetric manifolds. So let's start with examples. We have three spaces. So for the Euclidean sphere, the simple functions are polynomials. The T-simple functions are polynomials of the most T-restricted sphere. And there are many nice examples. There are some nice examples for spherical designs in low dimensions or for low values of this T. For instance, if you take the n-1 dimensional sphere Rn and look at the 2n points of intersection of the sphere with the axis, we get a 3 design. And the minimal vectors of the Lich lattice, the 100,000, 111,000 something, the minimal vectors of Lich lattice are a minimal 11 design in R. Okay. So nice sets of designs tend to be nice sets of points. And in fact, Korva and Sloan and Kohn and Kumar have shown that tight, optimal spherical designs necessarily have nice symmetry properties. So designs are nice things in the sphere. Okay, the second example is a Hamming cube. And here, T simple functions are just multilinear polynomials of degree at most T, restricted to the vertices of the cube. So basically they're spanned by monomials of the following form. We take a product, of xi's over sets of cardinality at most T. Right? Another basis for the simple functions are just the characters of the cube, which is supported on sets of cardinality at most T. So a T-design, it turns out that a T-design is a nice and familiar combinatorial object. In coding theory, we call it an orthogonal array of strengths T. This is coding theory notation. In combinatorics and computer science, we call it a T-wise independent set. So this is a collection of binary vectors whose restriction to any T coordinate is uniform, which means the following. So if I am writing all the vectors in my set, this is D, this is the T design. So this is the first vector, this is one vector. This is the second vector, and so on. And now, if I take any subset, not necessarily a contiguous, right, of T coordinates, then if all the possible 2 to the T vectors of length T, so one possibility is 0, 0, 0, another possibility is 1, 1, 1, yet another possibility is say 0, 1, 0, 1, and so on. I hope you see. So we have 2 to the T possibilities of vectors of length T, and each one of them appears in equal number of times. Okay, this is a nice combinatorial structure. And again, another way to say, an equivalent way, that if we look at the characteristic, right characteristic function of this set D, then its Fourier transform vanishes for all the low valued characters, if you want, except of course for the zeros character when we have the average of the set, the average size of the set. This is okay. So this is the second example. And the last example is the Hamming sphere. For the Hamming sphere, there is no good description of simple functions. We can describe them, the description is slightly harder, but then we do have a very good description of a design. A T design is just a combinatorial design or a block design, S lambda TKN. It just means a family of K sets which cover every set of cardinality the same number of times. Okay, this is due to Delsarte. And this is a very well studied combinatorial objects, and we have nice examples coming from finite geometries and so on. So in general, designs tend to be nice sets, and we want to construct them. Right? So the first question is, can we find designs? So let's start with the Hamming cube. In general, it's not easy to have good designs, to find good designs. I'm not saying construct, because usually we'll find them not construct. Right? So the Hamming cube is actually the easiest. Just for instance, of linear algebra, we can think about the Hamming cube being a space, a vector space of dimension n over the binary field. So let us introduce a new notion of a linear code. Linear code of minimal distance T is a linear subspace of the whole space, such that the distance between any 2 points is at least, right? It's the usual notion of arithmetic code, the binary arithmetic code. And Varshamov in the 60s observed that a random linear code, whose dimension is not very large, will have minimal distance at least. So we have such objects, and it's a very simple observation that if a C is a linear code and it's a linear subspace, if you look at the dual space of all the vectors orthogonal to C, then it's a T design in both directions. So this is equivalent, and since we have linear codes, the minimal distance T, we have designs of strengths. So we have, at least a randomized construction of designs, and for some parameters we can give specific designs. But one should say that usually we don't have neither code nor designs of optics.
Or excuse me,
Yes.
by random linear code you need to have to be just three basis vectors independent.
You mean how do I choose a random inner code?
Yeah.
I then just choose a geometric matrix. Right? Every bit is independent. So a geometric matrix of size k by x squared. Okay. So right. So we don't know neither optimal codes nor optimal designs. In some cases we do. Very good. Okay. So for the sphere it gets much harder. Delsarte, Goethals, and Seidel in 1977, after introducing the notion of T-design, observed by a simple application of Delsarte's linear programming method, which I will describe slightly later, that a T-design in the n-dimensional sphere has to have at least some constant times t to the n point. Here we should think about the dimension fixed and the strength going to t. So n is fixed and t grows. Until 3 years ago, the smallest designs, U2, Korevar, and Myers, had t to the n squared points, which is worse. The existence of designs was proved, I think, in the 80s by Seymour and Zaslavsky, but they had no estimates of the cardinality. This was essential proof. So Korevar and Myers, there were several improvements. Korevar and Myers had t to the n squared. And then 3 years ago, Bondarenko, Radchenko, and Yazovska showed an existence of designs with basically optimal growth, t to the n, by a very nice argument, a fixed point argument. And so now we have the right behavior dependent on the degree, but there's still an exponential n gap between the upper and lower, between the upper and the lower. Okay, so this is the situation in the sphere, the Euclidean sphere. And for the hemisphere, this is even worse, right? For combinatorial designs. So until this year, until this month, right, we didn't even know that there are these standard systems which cover every point exactly once, right? Every t point. So there was a progress due to Kuperberg, Lobet, and Peleg in 2011. They proved an existence of families of designs for a wide range of parameters. And finally, this year, Kivash proves the existence of designs for any values of lambda, t, and k, and n for sufficiently large n, of course, given sort of necessary divisibility conditions, some trivial divisibility conditions. So designs exist for every Joseph parameter. Right, solving the problem of Steiner from 1863.
53.
Okay, so right, so we have designs, but they're kind of hard to find. Okay, so in this talk we deal with a much simpler question of trying to prove that the designs have to be large, prove a possibility results. Right? Okay, so the best known lower bound for designs are obtained using the theory of Delsarte for codes and designs from 73. So let me tell you a little bit about this. So first, let me talk about error correcting codes. So we have already seen linear error correcting codes. So an error correcting code with minimum distance d in a metric space X is simply any subset of X for which the distance between any 2 points is at least d. Okay? In 73, in his thesis, Delsarte developed a unified approach which gives bounds both for codes and designs. Gives upper bounds for codes. The codes cannot be too large, and lower bounds for designs. Designs cannot be too small. One should add the designs were defined by Delsarte in the generality, right? There are a sort of natural notion in his theory, but then they capture, as we have seen, many natural things. Okay, so here is Delsarte's approach. We have a subset of a metric space, and we count numbers of pairs of points in the set at a given distance. So AI is we count points in X cross X at distance I, and we normalize by the size of the set. Right? This is very simple, just to have some experience with these numbers. So AI are definitely non-negative; they count something, and they are summing to the cardinality of the set, right? Because there are b squared pairs, and I normalize by b, so it has to be a sum to b. And A0 is 1, right? Number of pairs of points at distance 0, and just counting each point twice as a pair. So you have b pairs like that, so A0 is 1. And we capture this notion of a code. A code is a minimal distance d if you don't have pairs at distance 1 up to d minus 1. Great. All of these are linear constraints on AI. And B is the design of strength T if and only if AI satisfied a different explicit family of linear identities, which I won't give here, which depends on space. Right. So the main point of the South theory is that he gave an explicit family of linear inequalities satisfied by AI, which depend on the space. So taken all together, we obtain a linear optimization problem. We have these numbers AI, which satisfy an explicit family of linear constraints, and we want to maximize, to ask how large this could be. Okay, this is a linear relaxation of this combinatorial problem we're trying to solve. Right, this maximum would be an upper bound from the generality of the code, say, of the code, and for designs we get a similar, somewhat dual problem of minimizing the sum of AI given a different family of linear constraints. And using LP duality, we can pass to the dual program, and any feasible solution of the dual program would give us some bound for codes. And it turns out that all the best known bounds for codes and designs that we know are obtained by this approach, and basically they're obtained through the following a fundamental result of Machiavelli, Samorodnitsky, Ramsey, and Welch from 77. They gave a feasible solution for Delsate's dual linear program code in the cube, and in the Hamming cube, and in the Hamming sphere, in these two magic spaces, using the theory of orthogonal polynomials, which was suggested by Delsarte actually, that one should use this theory to do this, and this led to the best known bounds for codes in these spaces, and then this was extended a year later to this Delsate's approach to some symmetric manifolds by Kabakiansky and Levenstein, and this led to best known bounds for spherical and sphere packings in the Euclidean sphere and the Euclidean space, and in the projective spaces. Right? So this is the state of the art for codes. Right. Bounds for designs are for some reason slightly more difficult to extract using this approach. In fact, let me just say it as an aside, we are going to use metric structure of the space. Delsate's approach counts points and given distances. And we want to bound the size of the design, which is kind of not obviously a metric notion. Right? This would be something explaining why this is not very easy, something not proposed, but it took long time. So for the Hamming cube, one can apply the solution of Machiavelli, Samorodnitsky, and Welch basically directly, and this would give a lower bound for design as well, as an upper bound for codes. For the Hamming sphere, it took a while. Levenstein, 98, gave a solution which wasn't very far removed from other things. Anyway, it took like 20 years. And in 97, Euclidean extended Delsate's approach for designs to manifolds, and he gave best known bounds, lower bounds for designs in the Euclidean sphere and the torus, and the flat torus, Rn divided by z to n. And in 2009, Lubitsch extended the approach of Euclidean and gave bounds for designs for projective space. Right? So this is the history. You can see it slightly later for codes. And okay, so this is a philosophical slide. So how much time do I have when we start? Let's see.
You have more than 20 minutes.
So more than 20 or less than 25? Or
Yes, you do.
I see. Okay.
What?
No. Really? Then my clock is running.
25 minutes. 25 minutes.
25. Okay.
One more question. So in
Yeah.
terms of combinatorial designs, then what kind of bound are we talking about? Because one set doesn't discount precisely one, you know all the numbers, and you know how many sets you need to have.
So there are many parameters. So what I'm going to be interested in is the case, I guess, is the sort of when both T and K are linear. Okay, this is the okay. So Delsate's approach leads to best known bounds, and the question is why does it work so well, right? So at least to me it's not clear, and I talked to Delsarte, and it's also not clear. right? It's a very nice approach, but it's kind of mysterious. And so we get bounds for dimensional combinatorial objects by producing a feasible solution to a somewhat unrelated optimization problem, using somewhat unrelated tools, right? Which is slightly disappointing in a sense. Of course, this is something we do all the time in combinatorics, and I think this approach of Delsarte was one of the first examples of this linear obsession. Maybe the first. But still, somehow, one wants to prove this property of something, right? You get a bound, and to improve the bounds, which would be very nice, as a first step, it would be nice at least to understand the approach and the bounds better, at least to put them in somehow, wider mathematical context, to add some, maybe to add a different mathematical language to it. And so this is something, we're trying to do here. It works reasonably well, at least for designs. So here is a brief presentation of our results. So let X be a symmetric space. So it's a, either any distance regular graph or a globally symmetric remaining manifold, whatever it is. Let D, a subset of X, be a design of strength T. Let B be a ball of radius R, right? It's around some point. Then there is a radius which depends on X and the strength of the design, such that if we take a union of balls of this radius around all the points of the design, we cover a large part of it. Right? This is this metric approximation I promised you. And so in this sense, D approximates X not only in the analytic sense, but somehow in the metric sense as well. And in all the examples I gave, at least, to make this computational measure property, which tells us that if we increase this radius just a little bit, we cover almost the whole space. Right? And let me just say, going forward to the open questions, that there are reasons, slightly vague, the conjectures that it is for the MQ, the same radius should cover everything. It's not only an almost covering property, and maybe it's true for everything, for all the spaces. Okay, so we approximate metrically almost all the points in the space for a slightly larger. Right. So let me give an application and some details. So first of all, this immediately gives us a lower bound of cardinality, right? Which is basically the cardinality of the space or the volume divided by the cardinality of the volume. So continuous space is right. So, but we do need something, right, for this claim to be true and not trivial. For instance, if we take R to be the diameter of the space, this is very easy, right? So we need to say something about this area. So what we need, a necessary condition for what we need the Dirichlet eigenvalue of this ball to be smaller than the T's eigenvalue, right? Remember, so we're taking simple functions as the first T plus 1 plus 6. So we have eigenvalues lambda 0 up to lambda T. And we need something to be smaller than the smallest of these eigenvalues, which is lambda T. And the Dirichlet eigenvalue is for a manifold, this is the solution of the Dirichlet problem. Basically, we are looking, for the graph, basically, we are looking for the minimal, we are looking as a Laplacian restricted to the ball, right? Basically, or to the functions supported on the ball, and we want the function that has a minimum eigenvalue. Okay, does that make sense? And this we need to be smaller than lambda. And so, how do we get this? We get, for manifolds, we get this through the Courant's nodal domain theorem, which tells us that if you have an eigenfunction of the Laplacian, then every node, so what's a nodal domain of the function? So let's take a function, integrated to 0, it has negative, positive, therefore 0 values, remove all the zeros, the space decomposes, each connected component is a nodal domain. Right? So, and Courant's nodal domain theorem tells us that if you take an eigenfunction corresponding to eigenvalue lambda, then any of its nodal domains has eigenvalue, right? And for the graphs, it's even easier, right? You take an eigenfunction, the connected components of its positive values, and we get a special example. So we get an estimate of this on this radius that we want. It's very similar for graphs. And unfortunately, we get no new bounds this way. I'll say something. Maybe we get something slightly bigger generality. But this recovers in a very simple way all the bounds that I mentioned. And discovering properties Okay, so this is, I guess, this is the results, and then I still have some time to prove. So I'll pass, this is the end of the stories, I guess. So any questions so far? I'll
So
go.
this natural guess what this R should be always?
Well, I can say what we can have for this. Oh, okay, that's a good question. That's a good question. And okay, good. So one can, so I can guess that this R should be something that this R should give you, the conjecture right bound, at least for the Hemi cube. Yeah, but I don't.
So you believe that actually you cannot prove the right R, but it should be smaller.
I don't know that it's false. One can have the whole family of parameterized conjectures. Great.
So
And there is this kind of nice duality. One can think about all these, Fourier dualities. So suppose if a function is a function. So here is a conjecture which is related. If a function is supported or maybe code, it supports as large distance, then its Fourier transform has small coverage. It would be another dualization, right? It's like a double duality. Right? This is like that. Okay, so discovering problems.
So for codes, you often know what the covering radius is, right?
Sometimes, right.
Sometimes.
And also, I don't believe that if for codes for this dimension goes linearly. Right? For some polynomial codes.
Well, for range ornament, at least you know pretty accurately.
Do you know the exact?
The covering radius.
What you get is what you get. You get exactly the real lie of the regular chapter. Most of the
That's right.
Yes, at least for obvious stuff.
And you said that you believe that maybe
I don't
covers
know
the
that
whole
it's false.
space. Or,
I don't know that.
okay.
Okay. So, right. So this is okay. So this is same. So okay. So the proof starts with a paper, very nice paper from 2002 by Friedman and Killich, and I expected they won't have time. So they gave a very nice and elegant proof of this Makevich, Rodovich, Ramsey, and well, first upper bound for linear code to N cube. I have the proof here. Let me just go. I won't have to present it, but this was it. We have. So what I will have time for is to present our version of this proof, which we had together with Mikhail Tavon in 2005, which uses Fourier analysis of the Hamming cube, and then we are going to try and extend it for other spaces. So okay, so here's the argument, which is simpler than the one by Friedman and Killich, and it also extends further. So we start. Basically, the argument of Friedman and Killich is actually an argument for designs, not for codes. So let us start immediately with the design. We'll have a T-design in the We'll show this kind of property that for a certain radius, if you take balls of radius r around the points of the design, you get all this. This is what we want. And if you take, recall that if the design is linear, there is a dual space that is a linear code. So if you take the dual linear design, you get the first bound, the first Marlowe bound for linear codes. This is just by, so since we know that C dual, which is our design, is larger, basically up to some negligible factors in the size of the space divided by the size of the ball, linear algebra tells us that the code is smaller than the number. Right? Because the product of C times C perp is 2%. So we have. Right, so let's start with some preparations. We want to find, this is a crucial object we need, we want to find a non-negative function such that when we apply this Laplacian, this Laplacian operator to it, the function point-wise decreases by a small number, at most by 2. And we want it to have a small support, otherwise it's easy. Right, again we can have this, this Courant sort of model domain theorem function. We take a perturbed polynomial, which is a symmetric eigenfunction. A symmetric eigenfunction associated with the next eigenvalue, lambda t plus 1. We have these eigenvalues lambda 0 plus up to lambda t. We take the next, this following smaller eigenvalue. We take a symmetric function, which depends only on distance from 0, from 0. corresponding to this eigenvalue, and we restrict it to its positive values around 0. So it's positive at 0, it goes down, at some point it becomes negative, we only look at this ball where the function is symmetric, we only look at the symmetric ball around 0 where the function is positive. Right? This is our record. And then we shift it by all the points of the design. Right? We just any point of the design gives it a shift, an isometry of the cube, moving this function, we sum all of these shifts. Here is a crucial point, the Laplacian, in all the spaces we need, we want to deal with, commutes with isometries. So if I apply first an isometry to the function, right, and then I take the Laplacian, it's exactly as take the Laplacian. You see here, right, when I take isometries of the space, I have this operator of the function, right, it shifts. So for all of these shifted functions, we also have these properties. When I apply the Laplacian, the function increases by its most small number. And therefore, this also holds for the sum of these functions, for the function capital F. Yes, okay. Everything is very simple. Okay? And here is the Fourier-analytic part, which will be of similar degree of complexity. Okay, so as we have said, if you have a key design, and we take the characteristic function of the subset, everything is finite, we take the Fourier transform, it vanishes on all the small characters, except the trivial characters. And our function is proportional to a convolution of this, by definition, of this characteristic function 1 with set B with the function A. And therefore, as we know, convolution takes Fourier transform to products, and therefore this property holds also for capital F. It's Fourier transform, it's orthogonal to all the low to all the low characters. It has small Fourier coefficients vanishing, and therefore we have that the non-constant, the non-trivial component of F is spanned by eigenfunctions, by characters, supported on sets S which are larger than T, and their eigenvalues are larger than 2T. This was the idea. So basically, we have a function which, when we apply the Laplacian, it grows by at most twice T, but it's spanned by non-zero eigenfunctions with eigenvalue larger than 2T. The only way this can happen if it has a large constant component, right? So the inner product of F with itself is very close to its LP norm, right? It has a large part of the LP norm of F, and therefore, by trivial application of Cauchy-Schwarz, the support of F, which is the union of both around the design, is almost closed. This is the whole thing. Okay? Question. This is okay. So this proves this bound for the. This was the first linear programming bound. It's the best known linear programming bound for binary codes, and it could be extended to to the sphere and so on. Right. So this argument. Here is a vague phrase which says that this analytic argument actually could be seen to stay within the framework of Delsarte, just in a somewhat simpler way, but we not go into it. And some similar ingredients appeared in Euclidean 97 and Code 03. They also looked at Bessel functions, the zonal spherical functions for the Euclidean space, and they took them up to the first zero, and they did some forensic stuff with them. It seems different than what we do, for example, here. And this could be modified to recover general codes, to recover the first bound for general codes. But let me now talk a bit about extension to other spaces, which are not abelian groups, and we don't have Fourier. Now, this wasn't totally obvious to us because we don't have a Fourier basis. We don't have a nice basis. We don't have any canonical choice over a basis for Laplacian ideal spaces, which have large multiplicity, but we don't know how to do it. It's kind of difficult to approach them, and it turns out, however, that in some cases, such as the Euclidean sphere, we have a sufficiently strong group of isometries, and we can work directly with isometries. Okay, so here is a proof of spherical designs. This is the last part, and I still have time. Okay, so in the remaining part of the talk, let me try and prove to you this best-known bound of Euclideans for the Euclidean sphere using the same argument. So I want to show the covering property for a certain radius r. If we take spherical caps of radius r around the points of the design, we cover almost the whole space. So this would imply that the cardinality of the design is at least the volume of the sphere divided by the volume of spherical cap. And this, when one applies, one plugs in the right radius, gives this bound. The cardinality of the design is at least 2 to the n divided by n to the n times t to the power n minus 1. And this is the best known bound with Euclidean 97, which improved the bound of the Delsarte and Seidel by a factor of something like 4 over e to the n. This was improved. Okay. So here's the proof. So in the sphere, as opposed to the Hamming cube, we don't have any special point, right? We don't have a zero, so fix a point. This is our special point. This is the center around which we're working. And for any point of the design, consider any isometry, taking our fixed point O to this point of the design, right? We have many isometries like that. We take it. Now, so here is a crucial property of the sphere. There is a unique eigenfunction. So in any eigenspace of the Laplacian, there is a unique eigenfunction in this eigenspace called the zonal spherical function, which has the following property. First of all, it's symmetric. It's invariant under the group of rotations fixing O, right? It's symmetric around O. And the additional constraint, the point O, its value is 1. Right? We need to fix the value of O. So there is a unique function, and it's given, it's parameterized by the Legendre polynomial. Okay. So, and again, we take this function and we restrict it to the nodal domain of the point O. It's negative at some point, it's positive at O. We take the spherical cap at which it's positive around O and we stop there, and this is our function. And again, we define a function capital F. So now we apply all the isometries we have, right? We shift the spherical cap around all the points of the domain, and we get a function capital F. Questions? Anybody? Survivors? Questions? Okay, so this is the definition. It should be analogous to the definition in the cube. Right? We are almost done. So the support of F again is this union of the spherical caps. And again, it suffices to show that the inner product of F is sort of the eigenvalue of F. When I apply the Laplacian, the inner product of F grows by not too much, by at most lambda t, our smallest eigenvalue of the simple functions times the normal, right? And we need to show this, and also that F is orthogonal to all the simple functions, to all the non-trivial simple functions, non-constant simple functions. Not non-zero and non-constant simple functions, right? And this would imply that, again, that F has a large constant component, a large part of its norm is obtained by, the constant function, and therefore, again, by Cauchy-Schwarz, the union of the spherical caps to cover all these problems. So, right, so the first part is easy and slightly cheating, but the first part is obtained by some theory of Laplacian eigenfunctions on your manifold. It holds in high generality. You only need to have this one transitive group of isometries to get to any point of the design. Great. So let me tell you how to prove the second part. I want to show that F is orthogonal to any simple eigenfunction. Right? So let's choose one of those in some Vs for S between 1 and 2. And I want to show the inner product of F and phi is 0. Phi is this eigenfunction. So plugging in the definition of F, right? So I have this summation. This is the first. Right there. So the first part is the definition of F, right? And now this equality is just applying, a change of variables, right? To every point, I'm applying isometry inside F, so it's the same as to apply the inverse isometries inside P. It's the same, right? Great. So now F is invariant under the group of rotation, which fixes O. Therefore, I can replace any of those functions phi, by the integrals over this group, right? Okay, great. And this function psi, so this is the definition, I integrate it over the group, right? So alpha is over alpha running through the group of rotations. This function first apply, right, the isometry with respect to isometry alpha, then dz. Okay? So note that I'm integrating over a finite dimensional space, right? This is important. Applying as isometries, when I apply isometry, all these functions remain eigenfunctions with the same eigenvalue, right? So they stay the same eigenspace. Same finite dimensional eigenspace, eigenspace. The integration is easy. And now I claim that this function, so we have an eigenfunction in the same eigenspace, and which is invariant under the group of rotations. This integral is definitely invariant under the group of rotations. Therefore, it has to be some product, some constant product of this unique spherical function. And the constant is exactly the value of this function. Oh. Questions? Okay, fine. Therefore, we are done, right? So we have the inner product of phi of f and phi. This is, as we said, this is the inner product of f with all these rotated functions here, which is just the sum of their values at 0, at O, sorry, times the inner product of f and phi. Now the sum of, what's this sum? This is the sum of numbers, right? This is, so recall that psi is an integral of phi, but over all isometries which preserve O, right? So they don't move O. Therefore, it's just exactly, they don't change anything. Exactly the sum of values of phi at a point which is this isometry, original isometry tau z applied to O, which is exactly the sum of the points of phi over the points of the design, which is 0, right? And we are done. So this inner product is 0, and this finishes the group, right? And of course, this could be generalized, you know, to any rank 1 symmetric spaces like projective spaces and so on, obtained with the result of Lubitsch, and in higher generality to globally symmetric spaces of energy. It's slightly harder, but similar. Right? This is it. So, do I have like 2 or 3 minutes for questions? Yes. Okay, good. So the first question is this conjecture I asked about. The conjecture. So conjecture is say full heaven. So if I take the union over points of the design, these bows radius r, bows radius r around point z, I wonder whether this is the whole space X. At least for the hemicube. But somehow the feeling is that everything works very similarly, both for symmetric manifold and for symmetric graphs, at least for X being the hemicube. This is one question. The other question, which I say, at least for me, is more interesting, is to find an appropriate theorem for codes, at least a conjecture for codes. So, right, for designs, we have this theorem, right? Design covers the whole space, therefore it's large. So, what would be an appropriate theorem for codes, a conjecture for codes? I don't really know, but let me point out one interesting fact. So, I'm looking at this space of integral function over X, and I am sort of recovering eigenspaces 1 by 1, and so on, and I'm thinking about this, right? So I'm telling you more and more complicated functions in this space. So at some point, I go, far enough so that the subspace of functions I obtain sort of contains, so approximates eigenfunctions of a ball of radius d. Say in the hemicube, I fix a radius d in the hemicube. D is some delta n. A linear distance in the hemicube, and at some point, this space, the projection of a characteristic function of a Hamming ball of radius d onto this space, has a constant fraction of the L2 norm of this function. Right, notice that this space is invariant under isometries, therefore I can take a ball around it. So this space already captures a significant part of the L2 norm of this function. So if I take the dimension, so the dimension of the space is n to 0 plus n to 1 plus n to 2, right? This is a number. This number is exactly the first linear programmable group. So when I go high enough, to sort of to see this object I want to measure, this is a bound for, this is the bound we get. This is somewhat mysterious, and hopefully there is some mathematical at least conjecture hidden in this, but I'm not sure how to say it. If you do have something great, but yeah, do have something very, very mysterious. And
Thank you for your very interesting talk. So, are there any questions?
I have a question about what do you think, what is the minimum size design for a Gaussian curvature within manifold?
so, I don't think actually people look at this question, as far as I know. So if you add some parameters, I don't know, you have all these comparison theorems, right, I guess. But, so you can, I don't know. So people don't, apparently for many manifolds, people even didn't look at the question of the best spectrum, which is a simple question. Even a radius of a ball, how large a code against it? They just look at the volume bound of that. So,
I think the upper bound for the minimum size is the minimum number of vertices that are triangulation of this manifold.
for codes or for designs? You're talking about codes or about design? For designs you need lower
About
bounds.
design.
For designs you need lower bounds, right? Design should be large.
So I have an upper bound for the minimum.
So you see,
Could be interesting, I think.
So you can ask about weighted design,
yes.
and then everything is just Kara-Theodori or a...
I don't think the theory applies. I don't think this theory applies to the sort of.
So it will not give, but maybe, but one can get an upper bound from just dimension argument.
For codes, for designs, an upper
For
bound.
every
An upper bound,
design,
right,
an upper bound
right,
by Kara-Theodori, just
right.
by dimension. And maybe those...
There are constructions, right? There are constructions by, for weighted designs, it's easier, right? And I think
Yeah, it's easier to get them, but,
Yes.
but maybe the lower bound will
Maybe
show
harder
that
for lower bounds,
these
right?
are common or...
I don't know. Again, so the whole theory of, symmetry break, right?
Uh-huh.
So